Good afternoon, everyone, and welcome to this joint EOL-RAL seminar. It is my pleasure to introduce our speaker, Dr. Bianca Adler, who is a research scientist at CIRES, working at NOAA's Physical Sciences Laboratory here in Boulder. Bianca received her PhD in meteorology in Germany at the Institute of Meteorology and Climate Research at the Karlsruhe Institute of Technology, also known as KIT. Her research interest is in boundary layer processes, with one foot firmly in the observational realm, where she has participated in numerous field campaigns working with LIDARs, radiometers, soundings, and aircraft measurements. Her other foot is planted in the modeling domain, where her current research focus is on the synergy between boundary layer measurements and applications to renewable energy. This segues into her talk today, which studies wintertime cold air pools in the Oregon-Washington Columbia River Basin. This is an area that is home to a large collection of wind turbines and hence significant wind energy production. We are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located below this presentation screen. Do not be alarmed if you do not see your question pop up. We archive all questions until the end of the speaker's presentation, in which they will be revealed during the Q&A portion of the talk. Dr. Bianca Adler, we welcome you to EOL and RAL, and the virtual stage is now yours.
Yeah, thank you very much. Yeah, thanks for the kind introduction, and thanks a lot for this opportunity to give this talk here today. So I will talk today about persistent cold pools in the Columbia River Basin. And in the first part of my talk, I will use comprehensive observations to study the characteristics of such a persistent cold air pool. And then in the second part, I will use these observations to evaluate how well different model configurations do in capturing this cold pool. So before I start, just a few basics on cold pool. A cold pool occurs when a topographically defined depression, such as a valley or basin, is filled with cold, stagnant air, and this leads to an increase of air temperature with height. And this is illustrated here for a cold pool in the Salt Lake Valley. The cold pool is visible here by this polluted moist layer, and the temperature structure given by the red line increases, temperature increases with height to the top of the cold pool, and then it decreases. In general, there are two types of cold pools. There are diurnal cold pools, which develop under fair weather conditions during the night, and then they decay after sunrise due to surface heating. They can occur all year round. Then on the other side, we have the persistent cold pools, which mainly form during winter time, and they may last for several consecutive days, as daytime heating during winter time is not sufficient to mix out the temperature inversion. So clouds and fog are very common within persistent cold pools, and they modulate the vertical cold pool structure. And this is shown here in these two examples. So the temperature profile on the left-hand side is from a cold pool in the Colorado Plateau, which are very often non-cloudy. And as you can see, like stability decreases smoothly with height up to the top of the cold pool. Then on the right-hand side, the profile is for cold pools in the Columbia River Basin, and these cold pools are very often cloudy. So the typical temperature structure consists of a near moist adiabatic layer in the subcloud and cloudy layer, and then a very sharp temperature increase at the cloud top. For many applications, the decay of the cold pool is the most relevant part. And very often there are multi-scale processes involved in that. So these processes range from the smaller scales, such as bottom-up convective heating or top-down shear-driven turbulent mixing, to large processes on larger scale, such as upper-level cold air advection with the synoptically driven flow, or also like mountain waves and downslope windstorms, which form when the flow interacts with the upstream orography. And this can also lead to a horizontal displacement of the cold pool. So Cold pools are relevant for wind energy forecasting. This is because the wind in cold pools is usually light and variable, and then it rapidly accelerates during the cold pool decay. And this example, this is shown here in this example of a cold pool in the Columbia River Basin. So the top panel shows time height section of temperature, middle panel of horizontal wind speed, and the bottom panel of the wind power generated in the area. And you can see that in the middle part of this period, when the cold pool was present, horizontal wind speed was close to 0, and there was basically no wind power generation during the cold pool. Then when the cold pool decayed, wind power generation rapidly increased. This is because the relationship between wind speed and power generation is not linear, which is visible here in this turbine power curve. So we can see that here below the cut-in wind speed of this turbine, which is around 3 meters per second, there is no power generation. And then in the middle portion of the power curve, wind power increases roughly as the cube of the wind speed, which can lead to large jumps in power generations when wind speed changes only a little. And this happens here, for example, on the 4th of December, where we see this very rapid increase in wind power generation. So this relationship makes it challenging to integrate wind energy during cold pools into the electrical grid, and accurate forecasts of these cold pool events are very crucial. However, models still struggle with that, and this is partly because cold pools occur in complex terrain, which are challenging for all kinds of models. And the other reason is that there are like the multi-scale processes which are involved in the cold pool evolution, maintenance, and decay also impose a challenge for the models. So in order to address these challenges, the second wind forecast improvement project, short WFIP2, was initiated in 2015 by the Department of Energy. And the study area of WFIP2 was the Columbia River Basin in the Pacific Northwest in Washington and Oregon. This is indicated here by this red circle here, red square on the map. So the Columbia River Basin has not only a quite unique and complex topography, but it's also home to a very large amount of wind energy production. So at the time of the project, there were more than 6 gigawatts of wind capacity installed in the area. The Columbia River Basin is located to the east of the Cascade Mountain Range, which is a large mountain range stretching about 1,000 kilometers in north-south direction. And the only major outflow from the Columbia River Basin to the west is through the narrow Columbia River Gorge. So the southern part of the Columbia River Basin was the study area of WFIP2, with a lot of instruments installed in that area. So the overall aims of this project were to enhance the understanding of boundary layer physics and to improve the wind energy forecast in complex terrain. There were 3 integrated components to the project. The first one was a comprehensive field campaign lasting for 18 months. The second one were model development efforts, especially for NOAA's high-resolution rapid refresh model, HRRR. And the third one was the development of a support tool to assist the industry in wind power forecasting. There were 3 primary meteorological phenomena identified as the focus of WFIP2 due to their relevance for wind energy, especially in the Columbia River Basin. So these are, on the one hand, cold pools forming in the Columbia River Basin. Then there were gap flows through the narrow Columbia River Gorge, and mountain waves and wakes forming over the Cascade Mountain Range. In this talk now, I will focus on cold pools only. And this plot here shows the frequency of a cold pool occurrence during the 18 months of the campaign. And you can see that quite a lot of cold pools occurred or were measured in the Columbia River Basin, especially during winter months, which are indicated here by these blue shadings. And I will now focus on one specific cold pool case study from January 2017. And in the first step of the analysis, I used observations to study the spatio-temporal code pool characteristics and processes in detail. And then in the second step, I used these observations and what I learned from the observations to evaluate the performance of different HRRR configurations during this code pool event. So for the observational study, I used various instruments. So this is here an orographic map of the area with the locations of the instruments I used. So to study the vertical structure, I used different remote sensing instruments. So for temperature profiles, we used physical retrieval to determine the temperature profiles, and we did this at 2 sites. Like one was here in the Columbia River Basin, indicated by this red circle, and the other station here was at the exit region of the Columbia River Gorge. Today I will only focus here on the station in the center of the basin. And then for the horizontal wind profiles, we use data from radar wind profilers. There were several distributed in the area, and their locations are indicated here by the triangles. To get an idea of the horizontal structure of the code pool, we used near surface measurements of temperature and wind at surface stations. And these data I downloaded from the MesoWest repository. And there was quite a large number of stations in the area. So we had more than 700 stations measuring temperature and around 100 measuring wind. To get information on clouds, I had ceilometer backscatter profiles available here at Wasco in the center of the basin. And for the spatial distribution, I used the GZIP satellite product. So a key component of my study was to use the optimal estimation physical retrieval, which we call TROPO-E, to retrieve temperature profiles from the remote sensing instruments. So TROPO-E is based on a retrieval algorithm called ARIO-E because it was first developed for data from the ARIES system, which is a passive infrared spectrometer. Then over the years, it was further developed to include data from other instruments. And so the retrieval allows to combine data from various instruments. And in my case, I combined data from a microwave radiometer, from a radioacoustic sounding system, short RASS, and from a surface station. So the RASS is an active remote sensing instrument, and it has the advantage of a high vertical resolution and a good absolute accuracy. However, the measurements are limited due to the temporal resolution, with profiles usually on the order of like 1 hour, and also by the vertical range. So the lowest measurement range is usually a few hundred meters above the ground, and the maximum range is often limited to a few hundred meters, especially when the atmospheric conditions are unfavorable, which you can nicely see here in this example. Then, on the other hand, we have the microwave radiometer, which is a passive remote sensing instrument, and the instrument detects the brightness temperatures in the microwave range, which can then be converted to thermodynamic profiles. And this conversion is often done using statistical retrievals. The advantage of these instruments is that they deliver profiles throughout the whole troposphere with a rather high temporal resolution in the order of minutes. However, the downside is that the vertical resolution is quite limited, and elevated inversions are often smoothed or not detected at all. So when you look closely at these 2 time height sections of temperature, you can already see some differences. The RASS detected near height constant temperatures here in the center of this period, in the lower few hundred meters, while temperature decreased or increased with height for the microwave radiometer. So the stratification was very different in both instruments. So what we now did is we combined the temperature profiles, the visual temperatures measured by the RASS, with the brightness temperatures detected by the microwave radiometer using TROPO-E. And what the retrieval does is that it that it like combines the information from the different instruments, and it then tries to find the temperature profile that best satisfy the information from all the instruments. And then when you compare the temperature structure retrieved with TROPO-E, you can see that it's now different from the one obtained with the microwave radiometer alone. Like the stratification or the temperature in the lower few hundred meters now more resembles the RASS than the microwave radiometer. So Jalalova et al. Compared this inclusion of RASS, like the impact it has on temperature profiles in more detail and more systematically, and they found that like by including this RASS data in the retrieval, the profiles fit much better to radiosonde data, and the bias was like reduced by 10 to 20% in the lower 3 kilometer. And this here is just an example of a profile when elevated inversion was present. The red line is a radiosonde profile, and then the gray and the black lines are temperature profiles retrieved with microwave radiometers only. And you can see that they are quite smooth. And then the pink and the cyan line are TROPO-E retrievals when the RASS, different configurations of RASS were included. And you can nicely see that like this elevation inversion is then better captured with the retrieval. All right, so before we dig in the observations of the cold pool using the ground-based instruments, just a brief overview of the synoptic scale conditions. The red circle here indicates the location of the Columbia River Basin. And like prior to the actual cold pool formation, we had a cold front bringing cold air into the area from the north, which you can see here. Then after that, a high pressure system established east of the Cascade Range, and these are conditions favorable for persistent cold pools. And this high pressure system lasted for several days. And eventually a low pressure system approached the area from the northwest and bringing along like a strong southwesterly flow and the passage of several frontal systems in the area. And this finally decayed the cold pool. Okay, so let's have a look at the temperature and wind profiles in the Columbia River Basin. So I will start with some time height sections of temperature and wind, which we observed in the Columbia River Basin. Top panel shows temperature profiles and bottom horizontal wind profiles. So prior to the cold pool formation, this passage of the cold front, which we saw on the last slide, led to this cooling of temperature in all layers, which you can nicely see here in the profiles. Then, when the high pressure system established, this was associated with a warming above the mean ridge height, which is indicated here by this horizontal gray line, and cooling of the air below. So this led to the formation of a very strong temperature inversion with around 15-degree temperature increase over 1,000 meters. When you look at the horizontal wind profile, you can see that the flow in this cold layer was weak and easterly. And then associated with this low pressure system approaching the area, we can see this strong southwesterly wind and warm air, which finally occurred. And this strong wind and warm air slowly intruded into the Columbia River Basin, leading to a thinning of this cold air layer, and finally to a erosion of the cold pool along with this cooling in upper layers. So for a more detailed view on the temporal evolution and stratification, I extracted time series at 3 heights, indicated here by these horizontal lines. So the green line is at the top of the elevated temperature inversion. The orange line is at 300 meters above ground, so in the middle of this cold air layer, and the blue line is at the surface. So you can nicely see the cold pool formation with the increase of temperature here at 2 kilometers and the decrease of temperature at the surface. Now comparing the blue and the orange line gives us a good indication of stability near the surface. So during the first few nights of the cold pool, the surface temperature was several degrees colder than the temperature at 300 meters. So this means that we had a strong surface inversion. Then during daytime, the surface layer warmed, leading to a shallow convective boundary layer. Then in the second half of the cold pool, surface temperature and the temperature at 300 meters were very similar. So that means that we had a near isothermal stratification. So now to better understand the different stratifications we see within this cold pool, we selected 2 nighttime periods during which the differences in temperature were obvious. These are now backscatter profiles from the ceilometer. During the cold pool period, cloud base height is indicated as the black dots, and the black contours are isotropes. So the first period indicated here by the blue box was cloud-free, while the second period indicated by the orange box here, we had low-level clouds present with a cloud base around 300 meters above the ground. And when looking at mean equivalent potential temperature profiles during the 2 periods, we clearly see differences in stratification. So during the cloud-free period, we had a very strong surface inversion, while during the cloudy periods, stratification in the subcloud layer was near moist adiabatic. So as an indication of turbulence, we computed gradient Richardson numbers and turbulent kinetic energy dissipation rate for both periods. And we found that during the cloudy period, gradient Richardson numbers were very low in the subcloud layer, and dissipation rate was rather high. And this suggests that turbulent mixing in the subcloud layer was responsible for the difference in stratification we've seen in the lower part of the cold pool. So far, we only looked at profile measurements at one side. And while this is very useful, it doesn't tell us anything about the horizontal characteristics of the cold pool. So for that, we then used information from this large number of surface stations. And each circle here in this example indicates one surface station, and the color indicates the temperature measured at this station. The gray shading indicates terrain height, and stations with this white circle are located above the mean ridge height. So this is an example from the period when the persistent cold pool was present. And it's very nice to see that the coldest temperatures, here indicated by these purple blackish colors, are at the lower elevations of the Columbia River Basin. Then the stations above the ridge height here in the south partly measure temperatures more than 10 degrees warmer than stations at lower altitudes. Then when the cold pool finally started to decay, we saw in the profile measurements that warm air and strong winds intruded the basin. And this is nicely visible here in this in the horizontal distribution as well. So we observed strong winds and warm air on the southern slopes of the Blue Mountains during the period when the cold pool started to decay. Then 24 hours later, after a warm front has passed the area, like temperature at all stations in the area has warmed. But we still see that there was a shallow cold pool present at the lowest stations in the Columbia River Basin. So stations below around 300 meters still had experienced a shallow cold pool. So based on these observations, we think that there were different processes responsible for the decay of the cold pool. And we think that's a mix between large scale conditions, like when the low pressure system approached and mountain waves and downslope windstorms formed here over the southern orography, and also and turbulent mixing between the stagnant air in the cold pool and this very strong southwesterly wind above. Okay, so before we come to the second part of my talk, I would like to briefly summarize. So we used in situ and remote sensing observations to study a cold air pool in the Columbia River Basin. And we found that the cold pool temperature structure is strongly modulated by clouds, leading to with enhanced turbulent mixing in the subcloud layer and a near isothermal temperature structure. in our case, the cold pool decayed when a low pressure system approached the area from the northwest, which was associated with very strong southwesterly flow, and then warm air and strong winds slowly intruding into the basin. This warm air and strong winds first occurred on the slopes in the south of the basin, which suggests that mountain waves and downslope windstorms were present over the orography in the south. So the question is now, like, how well do the models do in capturing this persistent cold pool event? And to investigate that, we are evaluating different configurations of the HRRR model for this specific cold pool event. So the operational HRRR, as it's run by NCEP, uses this orange box here, encompassing the whole conus. For WFIP2, a smaller domain, two smaller domains were used. So one, which I call domain 1, encompasses the western conus and has a horizontal resolution of around 3 kilometers. And nested in this, we have domain 2 with 750-meter resolution centered on the Columbia River Basin. So one goal of WFIP2 was to develop and improve the physical parameterization and numerical methods in the model. So the tasks that were addressed during this effort included like the 1D turbulence schemes. So for example, the local mixing was improved. And now in case of very stable boundary layers, the mixing length is independent of height. It's what they call a C-less mixing length. And this helps to maintain stable boundary layers. The other thing which was improved was the subgrid scale clouds, which now better represents subgrid scale stratus, cumulus, and also help with the simulated shortwave downward radiation. Another thing under focus was the subgrid scale orographic drag and wind farm parameterizations. And then like several bug fixes and modifications now allow that horizontal diffusion in the model is now computed on Cartesian coordinates instead of model coordinates. And this strongly improves the maintenance of the cold pools by no longer mixing vertically when the model vertical coordinates follow the steep terrain. So this is an overview of the different configurations I'm comparing. The first one is what I call control. And this is the like a version which uses the pre-WFIP2 physics package. And this is what was run operationally at the beginning of WFIP2. The second version, what I call experimental, includes the physics improvements which were developed during WFIP2. And then the third version is very close to the currently operational HRRR version 4, and it includes many of the improvements of experimental. All runs use the same RAP data for initial and boundary conditions and are initialized at 0 UTC. So the control and experimental runs were done for the whole WFIP2 period, and they were like 24-hour forecasts. The version 4 runs were 48-hour forecasts, and they were done for the cold pool period only by my colleague James Kenyon. And I started off with comparing the first 24 hours for all 6 configurations. So for all 3 model versions and for 2 domain sizes with different horizontal resolution. So as a refresher, this is the time height sections of the observed temperature profile at Wasco with the persistent cold pool in the middle of the period. And on the right-hand side, you now see the temperature biases for the different versions. So one thing that sticks out is that the bias prior to the cold pool and after the cold pool decay are much smaller than during the persistent cold pool period and during its decay. During the persistent cold pool and the decay phase, all model versions have a warm bias except for the very lowest few hundred meters above the ground. So now to make it a little easier to compare all 6 configurations, I computed mean biases for 2 periods. So one for the persistent cold pool periods, which is here this 4-day period indicated by the dashed lines, and the decay period. So these are now like time or height sections of this bias with like configurations using domain 1 to the left of this dashed dotted line and configurations using domain 2 to the right. And you can see that by simply reducing the horizontal resolution, going from 3 kilometer to 750 meter, we already reduce our bias. So when the horizontal resolution is kept constant, we can see that there is a constant or a continuous improvement from control to experimental to version 4. So the bias gets smaller. However, even in version 4, we still see a pretty strong warm bias in all layers. And when looking at temperature profiles for the period with the persistent cold pool, we can clearly see that the vertical structure of the cold pool is not correctly represented in the models. In the models, we saw, in the observations, we saw this near isothermal layer in the few hundred meters above ground, which was related to the clouds. But in the model, this near isothermal layer is not present. Like, it's rather that temperature already increases near the surface. As a measure, but we also looked at the cold pool strength, and as a measure of that, we computed the heat deficit, which is basically the integral of potential temperature from the surface to ridge height. And we did this for the observations in black and also all the model versions for this grid point closest to Wasco, where we had the observations. And what you can see is that in general, the models did a pretty good job. They all captured like this increase of heat deficit when the persistent cold pool formed. And then they also captured the decay at the end. However, the heat deficit is generally too low, and this is related to the differences we saw in the vertical structure of the cold pool between the observations and the models. So when we look closely at the decay here on the 17th and 18th of January, you can see that the blue line sticks a little bit out. And this is the control domain 1 configuration. And it seems like in this configuration, the cold pool erodes too early. This is nicely visible here in these profiles. So the black line is the observation. Then the solid lines are model profiles at the beginning of this 24-hour forecast at forecast hour 3, and all model versions pretty much agree temperature-wise. But then at the end of the forecast period, 20 hours later, there are huge differences. So the control domain 1 version is now much warmer than the other configurations, which indicates that the cold pool was eroded too early. And this is even more visible on the 18th of January, where we see like here the blue line indicating control domain 1, which is several degrees warmer than the other cold pool, than the other configurations. This is also nicely illustrated when we look at north-south cross sections of temperature and winds through Wasco. So using, on the left-hand side, it's control domain 1. On the right-hand side, it's version 4 domain 1. You see at 3 UTC, so forecast hour 3, both model versions basically agree. But then 9 hours later, control domain 1 is much warmer, even down like to the bottom of the Columbia River Basin. And we think that probably improvements in the horizontal diffusion are responsible for this much better maintenance of the cold pool. Okay, so next thing we looked at are wind speed profiles. And these are now wind speed biases at different radar wind profiler sites. So there were 7 wind profiler sites in the Columbia River Basin. And I sorted them here like with increasing station height. Computing like mean wind speed biases for the cold pool period here in the top row and for the decay period in the bottom row. And when you compare the biases for the different model versions, you can see that not like at some stations, the bias didn't really change at all, like independent if we change the model domain, like the horizontal resolution, or if we change the model version, bias just stayed the same. At other sites, however, we did see an improvement when increasing the horizontal resolution or when going to newer model versions. So for example, here at Wasco or Golden Dale or Prineville. So we see here at Wasco and Golden Dale that we have the positive wind speed bias in the lower few hundred meters. And this is also present at 80 meters. So it has implications for the wind energy forecast. So these are time series of 80-meter wind observed in black, and then different model configurations in color. And the red horizontal line indicates the cut-in wind speed of a wind turbine. And you can see that like during the cold pool period, we oftentimes observed wind speed below this cut-in wind speed. However, the model wind speed was usually above this 3 meters per second. But we can also see that like when going to the newer model versions, this overestimation of wind speed got better, especially here for Golden Dale in the lower plot. Okay. So the next bias I investigated was the near surface temperature bias, and I used all these stations I showed in the first part of my talk and compared them to the closest grid point. So for a better visibility, I averaged values of stations which are within 100-meter height bins. And this top plot here shows a time height section of the near surface temperature observed at like all these stations. And you can nicely see that the cold pool period with the stations below the mean ridge height measuring like cold temperatures of less than -10 degrees, and then the stations above the mean ridge height were partly more than 10 degrees warmer. So now looking at the temperature biases for all these surface stations. And let's focus on the period with the persistent cold pool and the decay phase. So for all model versions, control, experimental, and version 4, you can see there's a clear dependence of the bias on station height. In the lower few hundred meters, all model versions have a negative bias. Then they have positive bias up to the mean ridge height and a negative bias above the mean ridge height. In addition, you can see that in the control, especially in the control configuration, you have a very strong diurnal cycle in the bias with a very strong positive bias during daytime. So to better visualize that for all 6 configurations, we computed 4 days, 24-hour composites using 4 days of the persistent cold pool. And so the left panel here shows control, middle panel experimental, and right panel version 4 for the 2 domain sizes. And it's very clear to see that this negative bias in the lower layer and upper layer was strongest in the control configuration independent of horizontal resolution, and that this diurnal cycle we saw in the bias is most pronounced during control, but also still visible in the experimental versions, but then pretty much not existent anymore in the version 4. And we think that these differences in bias we see is related to differences in cloud cover between the different versions. So because we don't have liquid water path, which includes subgrid scale and grid scale clouds in the control and experimental versions, we used long wave and short wave downward radiation as an indicator of clouds. So basically, a higher long wave downward radiation indicates clouds, and a lower short wave downward radiation is an indication for clouds during daytime. So these here are 24-hour composites of long wave downward radiation at the top and short wave downward radiation at the bottom. And what you can basically see is that long wave downward radiation increased and short wave downward radiation decreased when going from control to version 4. So this indicates that there are more clouds in version 4 and the least clouds are in the control run. So especially during nighttime, we see that in the control there was a like higher, lower long wave downward radiation, which indicates fewer clouds. And this means that we had a stronger radiative cooling, we had lower temperatures, and this can thus explain like this strong negative temperature bias we saw it during nighttime in the control run. The strong positive bias during daytime, which we see in control and experimental, can be explained by too few clouds during daytime, which allows then a too strong heating. But even so the bias is reduced in version 4, we still have biases in all heights. And we think that this might be related to the clouds still not being completely correctly represented. In the last part of my talk, I will now focus on comparing different forecast periods for the version 4 simulations. So I looked at 2 periods. The first one uses the first 24-hour forecast hours, and the second period uses forecast hours 24 to 48. So let's first look at temperature profiles. So these are 24-hour composites of temperature bias during the cold pool period for both forecast periods. So on left-hand side is forecast period 1, right-hand side forecast period 2. And we can see that the warm bias, which we saw during forecast period 1, is reduced for forecast period 2, especially here for the domain 2 simulations. When we look at mean temperature profiles for the cold pool period, we see strong differences, especially in the lower 500 meters. So the temperature profile for forecast for period 2 is much closer to near isothermal as it was observed. And this is why the bias is reduced in these layers. So when we look at cloud water and ice mixing ratio for the different forecast periods, as shown here at the bottom, it's evident that clouds are much more continuous during forecast period 2, during day and nighttime. When we look at forecast period 1, we see that during nighttime, the clouds were much less consistent, and they only intensify after sunrise, and then they persist throughout the day until like midnight, until the next forecast period. So the question is now, like, are the temperature profiles getting better because the clouds are better represented in forecast period 2? So to investigate this, we looked at 24-hour composites of liquid water path. The black line here shows the observations, and the green lines show forecast period 1, and the purple lines forecast period 2. So in the observations, liquid water path was quite low during nighttime. It slowly increased. It reached a peak at sunrise, and then it decreased again during daytime, indicating that the clouds dissolved. When we look at forecast period 1, we see that during the night, liquid water path agrees fairly well with the observed one. But then after sunrise, while in the observations, liquid water path decreased, liquid water path increased in the model. So this indicates that the cloud did not dissolve as it was observed. Then when we look at forecast period 2, we see that liquid water path is basically too high throughout the day, like during nighttime and daytime. It seems like the reduced temperature bias we see in the temperature profiles in the models, it's not because the clouds are correctly represented. We also looked at the cold pool strength for both forecast periods, like we did before. And I just want to point out 2 things here. So when we look at the evolution of the cold pool on the 12th of January, we see that forecast period 2 was too slow, or didn't capture this buildup of the cold pool very well. Like only after initialization on the 13th, heat deficit was higher. When we look at the decay period, we see that both forecast forecast periods did a very good job in capturing the decay. So the timing was very good, and also the rate of the decay was very well forecasted, even 48 hours in advance. Okay, so the last thing I want to present now is the difference in the near surface temperature bias for both forecast periods. So these are again these 24-hour composites of temperature bias for the near surface stations. And for the forecast period 1, we have seen this 3-layered structure with a cold bias in the lowest few hundred meters, positive bias in the middle layer, and then a negative bias above mean ridge height. When we now look at forecast period 2, we see that this negative bias in the lowest few hundred meters is replaced by a positive bias during nighttime. So we wanted to know if this can be explained by the differences in cloudiness we saw between the two forecast periods, and we used a liquid water path at the grid point closest to the surface stations for that. So what we did is we related the changes in liquid water path between both forecast periods to changes in the temperature bias between the both forecast periods for stations below 500 meters, for this lower layer here. And on the left-hand side, you see the distributions for domain 1, and on the right-hand side for domain 2. So what we can see is that a negative liquid water path change is related to a negative temperature bias change. And this basically means that at stations with a higher surface temperature in forecast period 2 also have a higher liquid water path, so that clouds lead to the change in the sign of the bias which we see. Okay, to sum up, so we evaluated 6 different model configurations consisting of 3 model versions and 2 domains with different horizontal resolution for 24-hour forecasts. And we found that improvements in the physics schemes led to a reduction of the warm bias in the temperature profiles and a high bias in wind speed profiles at some stations. But even in the newest model versions, there was still a significant bias in temperature and wind speed. We did find a reduction of near surface temperature bias at all station heights, but we also found that the bias of near surface temperature depended on station height, and old versions showed a strong diurnal cycle, which was removed in the newer versions. And we found that this improvement of the surface bias can be explained by more clouds in the newer model versions. In this second step, we compared 2 different forecast periods for 2 domains for the newest model versions. And was a little surprising at first that we found that longer forecast periods actually led to a removal of the warm bias in the temperature profiles in the lower few hundred meters. And this was because the temperature profiles for the second forecast period were closer to the observations which showed a near isothermal temperature structure. We found that these differences in stratification can be linked to more and continuous clouds during forecast period 2, but we also saw that liquid water path was generally too high in forecast period 2, so we had too many clouds compared to the observations. And the fact that the clouds were too high during forecast period 2 was related to the fact that the clouds did not dissolve in the afternoon of forecast period 1. So forecast period 2 started off with too many clouds. We found that clouds were also responsible for the removal of a cold bias at surface stations below 500 meters when going to longer forecast periods. That's all I have, and I'm happy to take your questions.
Thank you, Dr. Adler, for the insightful talk on observational and the modeling aspects of cold pool formation and decay. in the Columbia River Basin. We do have time for questions. Again, please use the Slido interface below the presentation screen to pose your question. Because this is a virtual one-sided seminar, I hope that audience members are judiciously crafting and typing questions on Slido. While we're waiting for questions, I have one. Do you know of other areas with wind generation that have these cold air pools? I wonder how unique this phenomenon is. Is it limited to the Columbia River Basin, or can your applications and methods be applied to similar regions with a suite of necessary instrumentation?
I mean, this method of analysis can easily be applied to other areas of complex terrain. And I mean, cold pools, they occur, well, all around the world if you have the right, complex terrain. I have to admit, I'm not familiar where exactly wind energy production is in the United States, and I don't know like if there are other areas with such large production in similar complex terrain.
Okay. It's a quiet group. Well, then I'll ask another question. With your liquid water path analysis that you showed, where the clouds don't dissipate during the day or at the height of the day, do you notice a cumulative effect in your biases over time between the model and observations? And if you cut the clouds, like at sunrise or at height, would that resolve the bias?
So what we see is that in the longer forecast periods, like basically this too many clouds we see, this is a result of the long forecast hours. So when we initialize again, this would not show anymore.
Yeah.
So yeah, but I mean, what I find a little puzzling is that actually the temperature profiles agreed so much better when we go to longer forecast periods, while the clouds agreed less. So there is still something which doesn't make sense to me, which has to be investigated further. So the models in general, they are doing really good, but there are still some things which are maybe better for the wrong reason. Yeah,
I saw that, and but I still wanted to just pose that question anyways, because that green line that you saw that just kept increasing and going opposite to the observations, I just kind of felt like cutting that off, and so I just wondered because it increased, but then it kind of settled down to a kind of a higher level than what it initialized at. So I just wondered if somehow reinitializing it somehow removed part of that bias. We are a very quiet group today. I can't ask all the questions. I'm an atmospheric chemist by trade. Come on, guys, help me out here. Well, I guess people can watch your seminar after the fact and then pose questions if they want to get in touch with you. Oh, we do have one question. Thank you. We have a question from Junkyung. Thanks for the great talk. What was the most important factor that contributed to improving forecasting while upgrading the version model?
Yeah, that's an excellent question. So one problem is that we had all these improvements combined in the newer versions. So it's not like I can say, oh, this like model improvement really led to the better forecasting of the code pool. We only had this one version where all these improvements were already like mixed together. But like by talking to the people who developed the model and improved like all these parametrizations, like we think that it's mostly related to these changes in horizontal diffusion, which really like helped over the steep terrain with the code pool erosion. but there, like with the runs we have, there is no way that we can like really answer this question for sure.
Thank you very much for that question. We have a question from Tim Myers. Can you comment on comparing station data to a single grid cell closest to the station? I wonder if other area averaged metrics may show different biases.
So, I mean, the problem is that we only have temperature profiles at this one site in the station, in the basin. So we cannot really compute temperature biases well, at more locations in the stations. However, I looked at the station at the whole basin, and I looked at like what's the clouds doing and what do area average liquid water path, how do they evolve, and they were very similar to what we saw at this one single grid point. So it seems like this one station, it's quite representative for the conditions in the larger Columbia River Basin.
Thank you very much for that question, Tim. We have a question from JW. Is it surprising that the cold pool decay was forecast well, although the strength of the cold pool was too weak in its middle phase?
Yes, I absolutely agree. And this is something, yeah, we also found very interesting. And it even seemed like this like differences in clouds we have between the control experimental and version 4, and which had this strong impact on stratification during the persistent cold pool period, they had no impact on its decay. So it seemed like for this specific cold pool case, the decay was really driven by large-scale processes, and the local stratification or the stratification of the cold pool only had a minor impact, or only played a minor role for its decay.
Thank you, JW. We have a question from Chris. Well, it's a comment. We see this problem arise often when modeling downslope windstorms in mountainous areas impinging upon cold pools. The WRF model with multiple physics packages and resolutions always seems to want to erode the cold pool too quickly.
Yes, and that's, I think that is a problem in the Columbia River Basin too. But for this specific cold pool, it seemed like, except for this like one version, like oldest model run with the largest horizontal resolution, all the other versions did a really good job in eroding the cold pool, and they didn't erode the cold pool too quickly. Like the decay, like the timing was really pretty good, which was a little surprising.
A lot of surprises in this one analysis. And it seems that the final word will go to Jung-Kyung, who says, thank you. And indeed, we thank you for giving this seminar. And we are about close to the seminar hour. If you are interested in Dr. Adler's presentation and have further questions, please reach out via her email, which is provided on the seminar flyer. On behalf of EOL and RAL, I would like to thank Dr. Bianca Adler on her excellent and informative and surprising presentation on persistent cold pool observations in the Columbia River Basin. Thank you, everyone, and have a great day.
Yeah, thank you.